Yes, sir.
My voice is clear today, right? Okay. So see, uh, so far we have actually studied the combination of the capacitors, parallel and series combinations, and that day we have taken some numerical examples, uh, which will be like sometime asked in board exam or maybe competitive exam. So today what we'll do, we'll just finish this chapter. We have two more sections to learn here. So one is the electrostatic energy stored in the capacitor, and another one is actually Van de Graaff generator. So those two we'll learn today, and then we'll try to pick up some few numerical examples depending on these topics. Maybe few numerical examples like examples from your book itself we can pick up. So yeah, so let us start our lesson today. So first topic is actually energy stored in a capacitor. How energy, this is the mechanism, like how energy stored in the capacitor. So this, yeah, this will learn. Actually, you know, like in your board exam, very frequently this question is being asked to derive the electrostatic energy stored in a capacitor. So that will be some 3 marks or 4 marks question in your board exam sometime. So I'll just explain how to derive that, and you'll see how capacitor gets charged. Uh, See, we have our all of us have our cell phones, right? So those cell phones have this kind of like capacitor, like the batteries they have capacitor, so which actually holds. So we have the capacitors, right? So which holds the charge, and we can use that uh, charge for some time. Okay, so the charge. Okay, so this should be, yeah. Just let my screen come. Yeah, good. So today's topic is, first topic is energy, and this energy is called actually electrostatic energy. Energy stored in capacitor. So this is the first topic we will learn. See, uh, we'll learn how the capacitors are being charged. So we take our model capacitor as parallel plate capacitor. We are not going to other geometries. First of all, we'll take up parallel plate capacitors itself. And see, if you want to charge the capacitor, what you should have? You should have an external source, that is the battery. So DC battery, okay? Or so suppose these are two plates, and you want to. So this is the capacitor. Initially, there will be no charge on the plates of the capacitor, parallel plate capacitor. So this is actually the condition, discharge condition. Discharge condition. That means there is no charge. Now, if you connect this with this battery, so what will happen? So this plate will be collecting the positive charges, and the other plate will be collecting the negative charges progressively, and it will be getting charged until, see, until, So this is the potential difference or potential of the battery until this, like potential across these two plates, okay, these two plates becoming the V, that means same as the potential of the battery. Until then, this capacitor will be charged. Okay, until then, this capacitor will be charged. After that, also see when you just plug your mobile and it gets fully charged. After that, even though you just keep it plugged in, that does not accept any charge, isn't it? It does not accept any charge. You know why? It is because the potential, see, there is no potential difference. So unless there is potential difference, there is no flow of charge. Is there any flow of charge? No. Until and unless there is a potential difference, there will be no flow of charge. So this is the practical. See, this is DC voltage. So sometime we'll be seeing that capacitors are used to block the DC, to block DC current or DC voltage. DC voltage or DC current. So how does that happen? So I explained now here. Block DC current means what? See, when current flows, so progressively what will happen? This capacitor will get charged and charged until its potential is becoming the potential of the, like potential difference between these two plates becomes the potential difference between the positive and negative terminal of the battery. Till then it will charge. After that it will not allow the current itself. Okay, so that's why see in the capacitor, the current actually in the capacitor, we'll see actually when we will be learning acid part, there we'll see again. So in the beginning current will be there. Okay, in the current will be, so current will be there in the capacitor. Okay, it will allow. See, if you have, suppose you have a circuit, resistor, then capacitor, then you connect this with a battery. So what will happen? Initially there will be current through the circuit. After long time, what will happen? After long time means this capacitor is denoted by C. After long time means until this capacitor gets charged, okay, fully charged. Then what will happen? So the potential difference across these two plates will be equal to the potential of the battery. So there will be no potential difference at this point. Suppose this is A and this is B. This is between A and B. If there is no potential difference, then there will be no flow of charge. That means there will be no current in the circuit itself. That's why sometime, not sometime, in every electric circuit, wherever we need to block the DC, block DC voltage or DC current, we use capacitor. Okay, we use capacitor. We'll see in the filter and all, we'll be using that. Okay, so that you will learn again later in the later chapters. Okay, so what was my agenda today? To know how this capacitor gets charged and what is the energy, stored energy in the capacitor. So suppose, as I said, initially we have to take uncharged plate. Okay, uncharged plate. Then you just connect. See, suppose this is plate 1, this is plate 2. Now you connect with the battery. Connect with the battery. This is the potential of the battery. Now what will happen? See, if this is the plate 2, so positive charges from this, see, actually it does not get charged immediately. What happens? Bit by bit, charges are accumulated on the plates, bit by bit. So some positive charge, suppose delta Q, gets stored here. Okay, positive delta Q goes here and gets stored over here. So becoming positive delta Q. And since positive delta Q has gone there, earlier it was neutral metal. There was no charge, neutral plate. Now see, neutral means what? Both positive and negative charges will be there in equal delta Q. Positive delta Q charge goes in this plate, plate 1. Then what is remaining over here? Minus delta Q. Similar negative charge will be accessed on this plate. Similarly, I think a situation when this like these two plates are accumulating charges bit by bit, and at some intermediate state, what happens? The plate 1 actually having charge q prime, okay, q prime. So this plate 2 or the conductor 2 will be having charge uh, minus delta q. Now at this situation again, I am just taking a bit of charge like positive delta q prime. I'm taking from plate 2, conductor 2 to conductor 1. So that's why the remaining charge in this will be this q prime q prime minus delta q prime. Okay, this is how I'm getting the charge bit by bit and putting on this conductor 1. This is the positive charge on the conductor 1, and same amount of negative charges will be manifested on the conductor 2. Okay, so this is how charging happens. Now this is the mechanism. This was the mechanism. Now you have to tell me what is the energy stored. So suppose the final stage, the capacitor can store maximum q charge. So in this way, bit by bit, charges will be accumulated on both the conductors. One conductor will be having positive charge, another conductor negative charge. Suppose the capacity of these two charges to hold charge q. Okay, so this is the final situation when it is fully charged. Fully charged. Okay, this is the fully charged situation. Okay, now you have to derive an expression for the energy, electrostatic energy. You have to derive an expression for energy. Okay, so let us derive an expression for that. So see, we are dealing with electrostatic field and potential here. Electrostatic field and potential. Do you know anything about conservative force or conservative force or something like that, or central force like that? Do you have any idea from your 11th standard? Okay, okay. If you don't have or you have forgotten, let me remind you. When when a force is directed towards a point or or directed away from the point, directed away from the point, from a point, that force is called central force. Okay, that is called central force. Or and central forces are always conservative. Central force, like gravitational force. The gravitational force, what they do? So there is a sun over here. So this is like sun, and this is suppose Earth or any plate like planet. So what happens? There is a gravitational pull, okay, and towards this. So the centripetal force that is actually obtained from the gravitational force, so which is always pointing towards the center, right? Pointing towards the center, right? Again, I have spring forces. Suppose spring forces, when you stretch stretch it or compress it, what is what this spring gives a force, right? So that is called spring force. So that spring force always acting towards its, always acting in such a way that the force brings the spring towards its equilibrium situation, okay, or normal length when it is actually compressed. what will happen? The force will act in this way to bring its normal position, and when it is stretched, then it will act this way, okay, towards its normal position. So the force is actually acting towards that. So spring force also another example of central force. And now what we are learning is electrostatic force. See, if I have Q1 and Q2, Q1 and Q2, two charges, the electrostatic or the Coulomb force, see, the force of repulsion is acting this way. See, force on, this is force on 2 due to 1. And now force on Q1, force on 1 due to 2 is acting this way. So it is directed away from the point charge. Okay. Okay. Anyway, so these are the forces which are called central forces, and central forces are conservative in nature. So another term you should have learned now in your okay. So this is conservative force. Conservative force. You might have learned in your work energy power, that chapter 11 standard. So whenever a conservative force, or whenever uh, a work done happens by the force, by conservative force, by conservative force, or against the conservative force, against the conservative force, that work done will be stored as potential energy. So this is, so the potential energy, the work potential energy is always related to that kind of force against which or by which the work done gets stored into the system. Okay, if you ask me, I'll give you one simple example. Suppose I have an object over here. Okay, so the gravitational acceleration, like the acceleration due to gravity is always downward, right? Now see, if I just want to just lift it up some h height. So suppose the mass is this, so what will be downward always due to this gravity. I'm just I'm just taking it to some height h. So what I have to do? I have to work against the gravity, right? I have to work against the gravity. So that work done is actually stored as potential energy in this mass. So the potential energy at this height is mgh. See, this is work done, right? Work done means what? Force into displacement. So what is the displacement and what is the force here? Force is mg on the block here, and what is the d? Displacement, that is h. So that's why this is mgh. This is nothing. This is nothing but the work done, which gets stored in this block as potential energy. So see, this is the gravitational force. We are acting against the gravitational force. Similarly, in this case also, when we act against the electrostatic force, then what happens? The work done we do to bring a charge. See, in this figure, this configuration, I am taking a small amount of positive charge delta q from this conductor 2 to conductor 1. So in this process, what I have to do? I have to do some work against the electrostatic force. See, electric field is in this way now. Electric field in this way. So you will feel an electrostatic force. What is that force? Force will be delta q prime into E, electric field. So this is the force, and we are working against. See, if this the distance is d, then we are working against this force. Okay, we are working against this force. So this work done will be stored in this capacitor as a potential energy, that is called electrostatic potential energy. So now we'll just derive the expression for that. Okay, so as I told, we have to find out the work done. Okay, so as I have mentioned again, I'll just repeat it. I'm taking a, see my situation, the initial situation was this: conductor 1, conductor 2, there was no charge. Now I just take bit by bit charges from conductor 2 to conductor 1. In fact, we don't have to do, if you just connect the battery, then that itself will do. Okay, that itself will do. So this is the external force. This battery is actually called the battery. What we are connecting with the capacitor, it is actually acting as external agency to work against the electrostatic force, which is developed here actually. Okay, in between the plates. Now see, initially there was no charges, so there was no force, no electric field, nothing was there initially. So what happens when you uh, like connect the battery? Slowly charge gets developed on both the plates, and equal and opposite amount of charges gets developed. So I'm taking an intermediate situation when the plate 1 is it actually hold, like it is already charged by q prime charge, and this by the conductor 2 is charged by minus q prime charge. Now what I'm doing, so see, at this situation when these two plates are having this q prime and minus q prime charge, there will be obviously electric fields, right? There will be electric field like this. Now what I'm doing, I'm taking delta q prime charge from conductor 2 and taking it to where? To conductor 1. So in this process, I am just doing a work against this electrostatic force. So what is this work done? How do we calculate this work done? So since I am taking an infinitesimal small, like infinitesimal charge delta q prime, so my work done also will be small only. Okay, this is dw suppose, or delta w, whatever you want to say. So this I have to find out. So how to find out the work done? See, if you remember from the definition of the potential definition of the potential is what? Work done per unit charge. Work done per unit charge is called potential. In few classes before I have discussed. In fact, in the beginning of this chapter, it is like what is potential energy, what is work done, all those things are there. Some of you have not attended those classes, but you can read. If you have any doubt, you can ask me again. So this is the definition of the potential. Okay, so since there is electric field, there will be potential across this two plates also at this situation. Okay, figure A shows that. So I'll use this formula to find out the work done. Okay, now now you might be asking, sir, what is the potential difference? If I don't know the electric field, how can I find out the potential difference between the plate? See, for that case, we have already learned there is a relation between uh, potential, then capacitor and charge. Yes, hello. Yeah, are you able to hear me? Anyone wanted to say something? So see, we have a relationship. C is equal to Q into V, right? C is equal to Q into V, or yeah, sorry, I am sorry, CV. Q is equal to CV. Q is equal to CV. So from here we can find out the potential. V is equal to Q by C. Okay, Q by C. So now the situation was Q prime. So Q prime by, so I'll take this as V prime, and this Q prime by C. Okay, Q prime by C. Okay, so see the capacitance of this capacitor. Okay, you might be thinking, sir, it is not yet fully charged. So how can you use this capacitance C? No, it is, you can see, like you can take that C for that capacitor. Okay, so now what we have got, I'll just clean and write. So the work done to bring delta q prime charge from conductor 2 to conductor 1 is dw is equal to v prime v prime into delta q prime. So what is v prime here now? V prime is q prime by c. This is your uh, potential and this is delta q prime. Now look, this is an expression for the work done when you take an infinitesimal charge from conductor 2 to conductor 1. Now if I integrate it, integrate this equation, then you can get the total work done. Okay. So that work done will be stored as potential, electrostatic potential energy between these plates. Okay. Let us see. So the final charge is how much? Q. So I'll write this here, q prime by c, and this is delta q prime. Okay. So if your delta q prime actually very small, delta q prime is infinitesimally small or tending to 0, then you can write this delta q prime as total derivative d. Okay. You can write this as total derivative d. If that delta q is very small, I'll just write that. See, when we write see, if I want to get, so this summation you have to write, isn't it? Summation. Okay. So this summation will be converted to integration if you take the limit delta q tending to 0 sum over this, then this will be converted to your integration sign. Okay, from the calculus. So this you can write like this. So that is what I'm doing now here. Okay. And this delta q you can write as total derivative delta d q prime, and this is q prime by c. Now see, if you just integrate it, what will happen? The result will be actually q square by 2c, right? This is the result. So this is the work done, q square by 2c. Okay. Now see, q square by 2c, this is the work done. So we can express this work done or the electrostatic potential energy. I'll write as energy itself, electrostatic potential energy as q square by 2c, and I have various relationship between q, c, and v. So I can express in terms of v also. Look, so I know q is equal to c into v. So I'll just put it here. So what I'll get the electrostatic energy, total electrostatic energy. So if I just put it here, so it will be c will be there, c square, and this is v square by 2c. 1c will get cancelled, so 1c v square, half c v square. Okay. Again, in terms of q, q is gone in terms of v. So this is the v in terms of v. Okay. So and you can even express in terms of v into q also. If you just replace this c by the other two terms, like c is equal to q by v, so you can express in terms of that also. So in that way you can express the, like in various form you can write this electrostatic potential energy stored in the capacitor. Okay. Look, I'll just show you in your book. You might be thinking, sir, you are teaching by your own. No, actually this is from your book. See, in your book there are few extra things. See, I have directly gone to here. I have directly gone to here after writing the infinitesimal work done. But what they have done, so they have taken the discrete charge delta q, and they can solve in terms of, see, in terms of summation also you can solve, and in terms of integration also you can solve. And in fact, in terms of integration you can solve it very easily. But if you write in terms of summation, you have to come all the way up to this stage. Okay. And you can find it out. You just you can avoid for your exam, you can avoid this thing, and you can directly go to here and uh, get the expression, because you will be having question of maybe some 3 marks or 4 marks. So this integration itself will be enough to write that. Okay. Okay. So this is the mathematical expression for the work done. And look here, this work done, since the electrostatic force, see, it is written here, whatever I have discussed so far. Since electrostatic force is conservative, this work is stored in the form of potential energy of the system. Okay. So for this reason, the final result of the potential is independent of the manner. See, the same work done you would have got if you just take the charges from, see, if you just change the polarity of the battery, if you take the charges from 1 to 2 or 2 to 1. So I have taken the positive charges from 2 to 1 such that the conductor 2 gets negatively charged and conductor 1 gets positively charged. If I would have done the reverse way, that means I take the positive charges from conductor 1 and put it on the conductor 2. Okay, so then also the energy would have been the same or work done will be the same. So this is because here the electrostatic force is conservative force, and for a conservative force the work done does not depend on the path. Work done for a conservative force, work done does not depend on the path. Okay, so see, yeah, so that is the thing. So that's why if you do in the reverse way also, nothing matters. Okay, now, yeah, so now we can show you that this work done in terms of electrostatic energy. See, how do we show that? See, we have got, so this is the work done which I have written the energy also, doesn't matter. So I can express that into in a nice form. I can write this electrostatic, actually electrostatic energy has, potential energy has energy density, in fact energy density, which we will be writing as U, energy density, that has expression 1 a half epsilon naught square. So this is the electrostatics energy density, electrostatic energy density. We'll get this formula or this expression uh, from our expression also. See, this work done, which is nothing but the total electrostatic energy, that is we have got q square by 2c, right? Now look, I have in the parallel plate capacitor what you have, C epsilon naught A by D, right? This is your expression for the capacitor. We'll just put it here and see what happens. So Q, in fact, I can, okay, I'll just let me write this first. Epsilon naught A by D. Okay. Now this Q is nothing but sigma by A, right? Sigma by A. I'm sorry, sigma into A. Sigma means surface charge density into A. This will be your Q. Okay. So Q square means sigma square A square. Okay, we will just put that also here. Let us put it here also here. So it will be sigma square into A square, and D will be already gone up. This is 2 epsilon naught. Okay, and here will be 1A. Now, so this expression, what we, if we simplify further, what we get is A 1A will go with this, so we will be getting sigma square A into D by 2 epsilon naught. So this we have got. Okay, so now say sigma, we have to replace the sigma with electric field. If you look in the parallel plate capacitor, so what is the uniform electric field set up between the two plates? That is E is equal to sigma by epsilon naught. Okay, sigma by epsilon naught. This is the electric field here, right? Inside the two plates, if the sigma is the charge density for the two plates, so this is electric field. So let us see, if I just put sigma from here, you will get sigma is equal to epsilon naught into E. We'll just put it here from there, so you'll get epsilon naught square, okay, E square, and this is A into D. I will tell you why I have kept this these terms inside bracket. This is epsilon naught. So look what I get is a half epsilon naught into E square into this term. So what is this actually? See, the parallel plate capacitor has area A and they have separation D. So this is nothing but the area under this. Sorry, volume under this capacitor. Okay, volume inside the capacitor, volume of the capacitor. Okay, that means this work done or the energy you see here now. This is the total energy in that volume of the capacitor. Now, energy density, electrostatic energy density. This is called electrostatic energy density, that is expressed in terms of U. So you have to just divide with the volume. Volume means again A into D. If I just divide that, then I get U. So this A into D is the volume, area into the distance or the thickness. This will give you the volume A into D. So if you divide this total energy with the volume of the capacitor, then you get the energy density half epsilon naught E square. Okay, so this is expressed by this. So this is called electrostatics energy density. Electrostatic energy density. Energy density means what? Energy per unit volume. Energy per unit volume. That is energy density. Okay. So you have understood, I hope. If you have any doubt, you can ask me now, or otherwise I will go to the next topic. So Kirtana, Mridula, then Nikhil, Priyadarshini, all of you have understood this. Have you understood? Okay, hope you guys have understood. If not, you can ask me anytime in any class. Okay, not necessary that this class you can ask. Okay, you can ask in any class. I'll let you know. Okay, but it will be very good if you can ask me now, because I have taught now. You have some idea at least now. You can ask me if you have any doubt. Or if you don't ask, then I will go to the next part of today's lessons. Okay, so now I think I'll move on to the next topic. So next topic is actually Venn diagram generator. First of all, let me tell you what is Venn diagram generator and what is the use of that. So Venn diagram generator is a machine. Okay, if you see this screen, here it is written very nicely in your book. So this is a machine that can build up high voltage of the order of few millions of volts. Okay, few million. That means 10 to the power 6, some 10 to the power 6 order of volt it can create. So this is a machine which can build up a high voltage, very high voltage, okay, of the order of millions of volts. And this resulting large electric field are used to accelerate the charged particles like electron, proton, ions, okay, to a high energy needed for experiments to probe the small scale structure of matter. And the principle underlying machine as follows. Okay, so like this Venn diagram generator is called, actually is one kind of particle accelerator. Particle accelerator. So where do we use these particle accelerators? We use particle accelerators in high energy physics. What is high energy physics? Nuclear physics, right? Nuclear physics, particle physics. Those are actually the topic of high energy physics, because if you want to know, see, still there is a research, okay, there is a research to know the God particle, right? God particle. So in search of God particle, what scientists are doing, like they are accelerating some charged particle to a very high energy. Okay, and there are also accelerators, particle accelerators they use. Okay, they use the particle accelerator. So you might be thinking, sir, what is this particle accelerator? We'll be again learning in our fourth chapter uh, the cyclotron. Okay, cyclotron, synchrotron. These are actually a particle accelerator. So I'll just briefly tell you what is particle accelerator. So we have seen that electric field. If I have electric field, and or maybe I have this again, I have discussed one topic here, that if there is a region where there is a potential, okay, or electric field in this way, so there is a potential difference across this two region, okay. Suppose x is equal to 0, x is equal to d. In this region, there is a electric field, okay, or there is a potential across it. So when a charged particle enters into this, a charged particle, suppose q, enters into this region, what will happen? That charged particle will be accelerated, okay, accelerated, and that see the and it will actually immediately gain a very high kinetic energy. How to calculate the kinetic energy? So q into v will be the energy. So that is equal to half m v square. So that will give you the velocity, how much it is getting after this. Okay, so you have some velocity v1, and when it leaves this region, it will have velocity v2, and that v2 will be actually much greater than v1. So particles are accelerated in this way. So when my electric field is very large, of the order of 10 to the power 6, then this charge particles will be having very large energy, because this is q into v. So you will have very large kinetic energy. And see what we do with this large kinetic energy of the particle, or what do we do by accelerating a particle? We have a material, okay, a material over here. I have a charged particle with very high speed and go and collide like this, okay. They will collide this here, okay, and there will be due to collision, there will be many things happening in this region. When you will like when you grow up and take physics as your major subject in higher study, you will learn this thing, okay. And here, when the interaction matter and this particle interaction happens, many informations will be coming up, okay. These informations will be studied in higher energy physics, okay. So this is actually the fact where we need a particle accelerator, and Van de Graaff generator is one kind of. So Van de Graaff generator is one kind of particle accelerator. Van de Graaff generator. Okay. Now we'll learn the principle of, first we'll learn principle of Van de Graaff generator. Then we'll go to the construction and the actual like Van de Graaff generator. I'll show you. In fact, I'll show you a demonstration from YouTube. Okay. So look, we have learned in the first chapter, if I have a conducting spherical cell, spherical cell. Spherical cell means what? Nothing is there. Nothing is there inside. Okay, nothing is there inside. So this inside, this portion actually is empty. Empty. That means if I put, so this is actually, see, if I can give you a simple example, I think a football. Okay, inside there will be only uh what? Volleyball, football. Inside there will be only air, right? Nothing will be there. No mass will be there. Only mass will be there on the periphery, okay, or on the surface. So this is like a football, which I say spherical cell, and this is conducting spherical cell. Conducting. So what is the property of conducting spherical cell? If you put a charge q over here, the whole charge will be distributed on the surface. Okay, whole charge will be distributed over the surface, and that distribution will be equally distributed. Okay, equally distributed over the surface. You might be thinking, sir, what is the relation between this and Venn diagram generator? We'll come to that. Okay, if I have a conducting spherical cell like this, then can you tell me what is the potential here, or what is the electric field over here? This will be 0. Electric field inside the spherical cell will be 0. What will be the electric field outside at r distance? At r distance, what will be the electric field? It will be q by 4 pi epsilon naught r square. Okay, as if this point, if I stay here, as if we will see that the whole charge is concentrated at the center. So from the outer point, you will see the whole charge is concentrated at the center as a point charge, So that's how you get the electric field at any outside point. You will get electric field as q by 4 pi epsilon naught r square. This is the expression for electric field for a point charge, isn't it? So this is the expression for electric field for a point charge. So when you calculate electric field for such conducting spherical cell, then electric field inside the conductor will be 0, outside it will be q by 4 pi epsilon naught r square. That means it will be acting as a point charge, like all the charge will be concentrated as if all the charge concentrated at the center. Okay. Now look, we know that E and electric field and potential has a relationship dV/dr. So if my electric field is 0, what I can say from that? If my electric field is 0, this side is 0, I can infer that V is constant, right? That means inside any point you choose, everywhere potential will be the same, and inside this region will act as equipotential surface. Equipotential surface. This will act as equipotential surface. Not only that, so if I ask you to find out the electric field, if I ask you to find out the potential, you could say that this is a equipotential surface. But what is the potential? Suppose the radius of this is r. Radius of this is r. Then potential at any inside point you can find out. How do you find out? You have to find out the potential on the surface of this spherical cell first. Okay, at the surface it will be Vr. Okay, that is actually q by 4 pi epsilon naught r. This is the potential on the capital R, obviously, on the surface. And see, there is no difference in the potential between any point and the surface, because the whole thing will act as a, up to the surface, it will act as a equipotential surface. So if you ask to calculate the potential at any point for a conducting spherical cell, okay, whose radius is given, charge on the surface is given, then you can find the potential at any point which is equal to the potential on the surface itself. So I get the potential on the like inside any point, the potential will be this. Even though the distance is less than r, you might be thinking this is r, means you will get the potential q by 4 pi epsilon naught smaller. It is not, because potential is constant everywhere till surface. So the potential will be the same, having the same value. Even if it is r1, it is r2. Okay, everywhere inside the potential will be the same as the potential on the surface. Okay, this is one concept. So this concept will come in our work. Okay, look now. So just a minute, I'll just clean this portion, or maybe I'll just clean everything. So we are reading, or we are learning the principle of Van de Graaff generator. Okay. So in the Van de Graaff generator, you will see there will be a big sphere, okay, spherical cell, and there will be a small sphere. This is sphere actually. This is not a spherical cell. This is sphere. Inside what you keep is a sphere, metal sphere. Okay, you have a metal sphere here like this, and it has radius. Suppose it has radius small r. Okay, it has radius small r. Now, if I want to calculate potential on the surface, okay, potential on the surface of this, okay, potential, this has radius capital R, and this small sphere has radius small r. Now suppose this small sphere has charge on its surface small q, and this has charge capital Q. Okay. Now what is the potential uh, on the surface of this small sphere and on the surface of this capital sphere, spherical cell? That means what is the potential this, and what is the potential this? We want to calculate the potential. Can you tell me what will be the potential at this point? If I say this is a point P and this is a point, suppose this is S, okay, on the surface of the capital H. So what is the potential at this P? So potential at P will be actually the potential due to this sphere itself. So that will be small q by 4 pi epsilon naught small r, and the potential due to the capital sphere itself, spherical cell itself. So everywhere that is same. What is that? Q by 4 pi epsilon naught capital R. Do you agree with me or not? You have to agree. Okay. Okay. So now another point. Okay. So I think this. Yes. Oh, this is all right. All right. Now see, I'll write the potential at S. So potential at S due to small q will be q by 4 pi epsilon naught capital R, and for the spherical cell will be this much only, q by 4 pi epsilon naught R. Okay, this is the potential at P and Q. So what is the potential difference? What is the potential difference then between these 2 points P and S? So potential difference I can write Vp minus Vs. Okay, let me check what is the potential difference. Look, I just take the difference between these two, right? So what are the common terms? So this is one term and this is one term. So this will, so these are the common terms, they will get cancelled. So what you will get is actually q by 4 pi epsilon naught. This is common for both the cases, and you have this as 1 by small r minus 1 by capital R. Do you agree with me? This will be the potential difference. Now look, this small r, this, see this r like small r is always less than capital R, isn't it? That means what? This term will be always greater than this term. That means what? This potential difference will be always positive. Positive, okay? Always positive. So then what will happen? If this happens, what will happen? So charge will flow. Charge will flow. So in which direction charge will flow? Charge always flows from higher potential to lower potential side. So how charge flows? Charge flows from higher potential to lower potential side. That means what? That means what? You have a bigger sphere, you have a smaller sphere. Whatever charge you put over here, so that will be getting transferred to the capital sphere, right? It will get transferred to capital sphere. Okay, so the charge will be some q prime, suppose. So this will be okay. So it will get the charge because this is having higher potential. Vp is greater than Vs. Okay, so always charge flows from higher potential to lower potential side. So this is how you look if you have a small sphere inside a capital spherical cell. If your q is greater than, like, as much as you put the charge on the small sphere, that will actually flow to the outer spherical cell, and that will get distributed uniformly over the surface of the spherical cell, outer spherical cell. And this is how, when there is a charge difference, there will be a huge potential difference across this. Okay, there will be a huge potential difference developed across this. Okay, around the region, there will be a huge potential difference, or very high electric field will be generated by this way. Okay, okay, so let us see the same thing in your book. See, it is here. Okay, if you somehow connect this small sphere to capital sphere by conducting wire, then charge will flow from small sphere to capital sphere. Okay, so this is how we can generate, like, we can develop a huge potential difference across these two. Okay, okay, so this is the principle for Van de Graaff generator, to develop a huge potential or high electric field or high potential. And that high potential is needed for what? Needed to accelerate charge particles. Now look, I'll tell you the experimental arrangement here. Experimental arrangement or the construction of this Van de Graaff generator. So this is the principle of Van de Graaff generator, and it is a machine capable of building up a potential difference of few million volts and fields close to breakdown field of air. What do you mean by breakdown field? I had actually discussed some time back in the capacitor part. What do you mean by breakdown field of air? Air is insulating, right? They don't have any free charges. But when you apply, or when you create a very high field of the order of 10 to the power 6 volt per meter, in that electric field, what will happen? Uh, air molecules will be ionized. That means electrons will be pulled out from there. And when they get ionized, then they no longer become or behave like insulator. They behave like, then they behave like conductor. That is the breakdown of the air. That is breakdown of the air. Okay, sometime in air, if you just create a very huge potential or electric field between two sharp edges, you will see some spark. Okay, you will see some spark. Okay, all right, so see here in this arrangement, there is a uh, there is a large spherical conducting cell of few meter radius. Okay, is supported at a height several meters above the ground level, several meter above the ground. Okay, see here, this is the huge sphere of having radius some few meters. Now see this support column has to be insulating column. Okay, insulating supporting column has to be there. Now a long narrow endless belt, see this, the deep blue, see this is actually belt, and this is insulating belt, rubber belt or some other insulating materials belt. And there, that belt is actually endless. That means it is supported by two pulleys, and it can just rotate. Okay, it can see the bottom part can go to up part up, like top part will come bottom, like that it will be rotating. Okay, in a cycle. So a long narrow endless belt belt insulating material like rubber or silk is wound around two pulleys, one at the ground level, one at the ground level, okay, and one at the center of the spherical cell. This center of the spherical cell. Here, see, this belt itself actually acts as the small sphere, okay. Here there is no small sphere as such. Here there is what you have. Actually, you have to create a high potential. That we'll see. There is an arrangement for that. Okay, high potential difference will be created by this accumulating charges. Okay, we'll see what is the like action of that. So now what happens? You know, this belt. Okay, this belt is kept continuously moving by a motor at the lower pulley. Motor is here set. Okay, this motor will be pulling this lower pulley. So lower pulley, like the belt with lower pulley will be actually pulling the other pulley also. Okay, rotating the other pulley. So it continuously carries a positive charge spread on it by a brass and the ground. See here actually, so there is a metal brass, or you can say, yeah, kind of comb, actually metal comb with a very huge uh, potential difference across those. So what will happen? The charges will be created over here. Positive charges, negative charges, all will be created. So positive charges will be actually carried by this belt from bottom to top, and when it comes here, there is another brass, metal brass, which will actually uh, take the charges from this belt to this capital sphere. Okay, I'll now show you a small video. I think, yeah, in the YouTube, and then you'll look if you can appreciate that. Just a minute. Yeah, I think this is the one. Okay. Okay, just a minute. I'll go here. Yeah, let me go here. Oh my God. Okay, let me. Oh, I'm not going to, and I'm not able to go there. But anyway, if you search in your in your mobile, in the YouTube, you can see this nice demonstration. In fact, I wanted to show you guys. Just a minute. I'll try to get it somehow, and then I'll stop this class. Okay, with this small demonstration video. Let me see if it comes. Okay, nice. Yeah, it has come. Okay, so look here. There is a, like, I think this is 3 minutes video. Okay, just a minute. You just see. This is from actually Scholars Wing. We should acknowledge this site also. Why is that gone? Okay, just wait for a minute. I think it will play now. If unfortunately it doesn't play, then I will request you people to see this demonstration. Okay, uh, in your mobile. So then you'll be able to understand or appreciate the working principle. Okay. See this yellow one. You can see this is the belt. Okay, and this is the, see, this is the upper part. Okay, inside the sphere. Okay, inside the sphere, spherical cell, upper part. See, when the charges come with this belt, and here they will get stick to this. This is another metal brass, or this is called kind of metal comb, and it is connected to the outer sphere. Okay, and that's how it goes to, charge goes to the outer sphere. I think, yeah, I don't know, somehow it is not getting played. Uh, Dear students, I will ask you to see such kind of demonstration video so that you can understand the working principle, how it works and all. Okay. you just can write in your YouTube Venn diagram generator, and then you can easily get such kind of videos. Okay. So I think I'll stop this class here because it is not getting played. You just search. Oh, now it is okay. It has come now. Okay. So just listen, just 3 minutes video. Okay, so this was the small demonstration video. I think you can see again in yeah. Okay, so Priyadarshini, if you are not able to hear the video audio part, so please note down this Scholar Wings. Okay, this website, and see, you just type in your YouTube, you will immediately get it, and please listen to this and please see this video. Okay, then it will be very much understandable. Okay, otherwise the theory will be very much abstract. Okay. Okay, then I'll stop the class here. All right.